Hello, my name is Martin Wakeman. This talk is on nuclear plant information models and their application to the management of knowledge throughout the nuclear life cycle. In particular, it focuses on new nuclear build projects and talks about how the knowledge of the engineer, procure and construct organisations can be passed over to the operating organisations who may be operating the power plant for the next 70 years. My own experience is that I have been involved in delivering information systems to 16 operational nuclear power stations, decommissioning plants, and in 3 nuclear new build projects. I hope you enjoy the following presentation. We live in an information-rich world. All the world's knowledge is available to me at the click of a button. If I've never built a garden shed and I want to know how, then a quick search of Google or YouTube will present me with a video of how to build a garden shed, put there by experts. Experts and knowledge from all over the world is available to me. The problem, of course, is in sorting out the truth from the not so true, the good advice from the bad advice. But in general, I can make that judgment by looking at a few different sources. All the knowledge is there, but can I find it? There are some apps that we trust more than others, and often we will research 2 or 3 solutions before deciding on a course of actions. I live in the United Kingdom and we are obsessed with weather, and I will look at 2 or 3 different weather apps, then decide on which one I'm going to believe. Normally, it's the one that says it's not raining. I don't have to be any good at reading a map anymore. The GPS in my car will tell me the way. Artificial intelligence can even help me in diagnosing the symptoms of my illness without going to a doctor. By contrast, most of the nuclear world is stuck with knowledge hidden away, mostly in documents, or held in some legacy computer system that's difficult to find or use in a way that the system wasn't designed to do. Or the knowledge is held in some expert's head, but I don't know which expert. Or I find it out during a meeting or during training, and then it's in my head and not in my colleague's head. But because that knowledge in a document or in training was put there by an expert, then it's probably correct. However, is it correct? When was that document written? What has changed since it was written? We will rightly adopt a questioning attitude. So when dealing with knowledge management in the nuclear world, we should be looking at how we can learn from the technology that is available to the rest of our lives. And the key to that is data. And by data, I mean not just the bits of unrelated chunks of information that we find in computer systems, but videos, diagrams, connections, integrations. Imagine the power of Google and YouTube being available to all inexperienced nuclear operators and maintenance staff. Being able to draw on the experience of experts because they had converted their knowledge to data. And I am a case in point. I am mostly retired now, apart from the odd consultancy. But there is lots in my brain that nobody else knows. I have left 3 different nuclear companies 4 times. But each time, there was no mechanism for extracting my knowledge before I left, apart from the work I was undertaking at the time. This is both a technical problem and a cultural problem. Why don't we pay our staff to create video snippets that can be available on a company YouTube channel? Why is there a reluctance to share our knowledge with others? Is it because my knowledge sets me apart and is the reason companies will employ me? So there is a knowledge management issue for existing nuclear operators. In how can we ensure that the knowledge that is wrapped up in people's heads, in documents, in old computer systems, can be extracted into a format that can be used for others? And this is a cultural as well as a technical issue. However, what I want to turn to is specifically for new entrants in the nuclear market, for those embarking on new builds. You are looking at a very long nuclear life cycle ahead of you. You may be right at the left-hand edge of this diagram. how do you possibly plan to ensure that the correct knowledge is available throughout the lifespan of this thing you are planning to build? When that knowledge is developed by different organisations in their own computer systems by their own staff. Often, the people who will operate the station will only be recruited and trained in time for commissioning. What happens to the knowledge, the information, the data held in design systems, from manufacturers, from constructors? How is that knowledge passed over to the operators? Will it be done using paper, via PDFs? Will it be done at all? Here is the same picture drawn slightly differently. These are the building blocks representing the life cycle of a nuclear power plant. Starting with the left-hand side, we start with the requirements that include not only the owner-operator requirements, but those from the regulator or from any local or community planning commitments that the builder of the nuclear power plant has to meet. Then you have the design process. The design may be performed centrally by one design organisation, coordinating the NSSS design, the turbine island, the admin buildings, the roads, the networks. But often, different organisations may be involved, and it may be unclear who will stitch the design together, or even agreeing on standards between these organisations, each with their different computer systems. That may be difficult. Once the design is done, the next stage is to construct, buy or manufacture the elements of the power station and put them together. You will construct some parts, the building, the concrete. You will buy other parts. You will manufacture other elements. Many different organisations will be involved, each with their own IT systems and standards, and none of them will be pleased about handing over information to the operator. I won't go into the rest of the diagram, apart from pointing out that even whilst in the operational phase, different organisations may be responsible for, say, any ongoing design changes to the nuclear elements. So the life cycle actually looks something like this. The picture is more fragmented. Many different organisations using many different computer systems are responsible for different parts of the life cycle. But the customers, the operators of the station, need information in a consistent and coherent way. So how can we ensure that the suppliers of the power station, the designers, the constructors, the manufacturers, provide the information in a consistent and coherent way? My point is that the operator needs data. It needs data to maintain and operate a safe and effective and efficient power plant. It needs everything that the combined EPC organisations can provide. Because the alternative, which actually happens even in power plant being built today, is that the operator has to employ an army to collect that information. The information is made available, but the default is to offer all the information in the form of PDF documents, which brings us full circle in that the knowledge is being hidden in documents. So, at the same time as building the physical plant, you have to make sure that you can also build the digital plant. You cannot do this alone. You need cooperation and commitment from all elements of the supply chain, the designers, the constructors, the manufacturers, the decision makers, the safety engineers. But what is the digital plant? We use a term in the nuclear industry called systems, structures and components. This term encompasses the structures, the buildings, the rooms, the steelwork, the pipework, the components, the pumps, the motors, the valves, the cranes, the turbines. Between them, the structures and the components represent all the elements of the power plant, and the systems is how these components and structures are all put together, how they work with each other to make the power plant operate. The digital plant is everything associated with these systems, structures and components. The drawings and documents, the 3D models, the manufacture details, the maintenance and engineering history, what function the item has, how it relates to other items of plant. The decision making behind the item. What are the requirements? What is its safety function? How is it constructed? Its spare parts, its maintenance and operating instructions. Ideally, in the digital plant, all this information should be readily available and understandable to anyone, How then does the owner-operator get this information, this data, this knowledge on day one of operations? It needs, first of all, to establish its requirements in all of the contracts it has with the EPC companies. Each contract must have the data or digital plant requirements and expectations built into it. The Buildings Information Modelling BIM process, embodied in PAS 1192, now rebranded as ISO 19650, can help create a framework for data delivery, what data is required and when. But you, as operators, must also establish how you are going to collect and verify that data and how you are going to build your digital plant. For those of you coming into the project from the construction industry, you may be aware of the BIM process and wondering how this aligns with these principles. The BIM process, however, does not give a silver bullet solution. The difference is in the sheer size and volume of what we are requiring from a normal BIM organisation and the importance of it. The data we are asking for is greater than what BIM wants, and the level of complexity of the models is far higher. But what data do we need to collect? How can we, the operators, specify what should be in the digital plant? This is a simplified diagram representing the total IS and IT map that needs to be constructed for a new nuclear power station. The asset data, systems, structures and components, is at the core of this diagram and gives the basis for integration between all IT environments. I don't really want to scare you at this point, but you can use this map to liaise with your data and IT suppliers to establish what each is capable of providing. To achieve this, we need to build the physical architecture, the networks, the servers, the integration hubs, the laptops, the mobile devices, the desktops, the information systems architecture, systems, interfaces, master data management, processes, workflow, a security architecture, especially around integration with IC protection and control systems, people trained, system administration and support arrangements in place, data to fill all the systems and to ensure that the station operates safely, effectively and efficiently from day one. This is a huge task. The last diagram represented the power plant from a functionality point of view. This diagram begins to map the data requirements of a nuclear power plant. It is not complete, but a good representation of the information needed. It has at its core the concept of systems, structures and components, identified at the center by the functional tag, the identification that describes every element of the power station and what it does. I won't go into too much detail about this diagram here, but you will have a copy of the slides to study and adapt to suit your own circumstances. Each of these small lines below the circles represents the attributes to be collected for each entity, and I will expand on these in the next slide. There are a number of considerations in identifying the data that has to be collected in a new build situation. Firstly, there are the types of data. Identification, basic identification, the entity name, description, classification, the safety class, critical equipment, fire equipment, containment closure, environmental classification, the dimensions, height, length, depth, weight, location, where is it, specification, design information, what must the component do to meet requirements, the discharge pressure for instance, the temperature range, the operating state, etc. Then we have the information that we need to get from construction, manufacture or procurement. Then installation information, commissioning and operations, testing information. Some attributes are generic or specific to the component or structures involved. When I worked for Horizon Nuclear in the UK, we had identified about 2,000 separate attributes from examining different standards and our own experience. Of course, not all of these attributes must be collected for all structures and components, and will depend on the importance of the component, based often on the classification. You will need more information for a safety-related component, for instance. In conclusion, what I have given you are the ingredients with which you can build a plant information model. The work of EPRI a few years ago, and of the IAEA, has tried to push for a nuclear standard methodology in this area. But whilst these documents are very good sources of background, the formulation of a worldwide PIM standard for new nuclear builds is some way off. The work that I and a few others were doing at Horizon Nuclear in the UK was probably going to be the best example I have seen of building a PIM. But unfortunately, as with many nuclear projects, the build has stalled and is unlikely to proceed. Which brings us round to the beginning of this presentation. How do we capture the knowledge that was in that project and others? So why do we need all this data? The economics of a nuclear power plant are simple. As most plants around the world operate as baseload, if a plant is operating, it is making money. If a plant is not operating, it is losing money. So the aim is to keep a plant working for as long as possible. This means reducing outages, planned and unplanned, spotting problems before they occur and taking action. And when they do occur, taking action efficiently and timely. Faster, more efficient maintenance. Faster and more efficient engineering design changes. I could go on. In this presentation, I have deliberately not focused on the technology involved in building a PIM. Many companies, Intergraph, Dassault, Siemens, PTC, have all built up their suite of systems and provide software capable of building a plant information model which uses a 3D model to provide a portal into all other information, knowledge and data based on the plant items. And no doubt, their salespeople will demonstrate how this will all work in a perfect world. However, in my opinion, buying the technology is easy, and all the leading vendors have a solution to fit. What is difficult, though, is filling this software box with the data that the owner-operator will need when most of these systems have been built for the design organisations. I'm going to finish by looking at how a data-rich environment might be used in the future. For instance, using augmented reality. Information from sensors could be displayed on a VR headset embedded in the operator's helmet, so that operators could instantly spot issues whilst out on the plant. Not only real-time information, but plant identification details, isolation details, defects could all be available on a heads-up monitor. Tools, spare parts, consumables could be delivered to the point of work using autonomous vehicles dispatched from the storeroom just in time to work on maintenance activity using an inbuilt 3D map. At some point in the near future, maintenance robots could be dispatched to work in some of the more inhospitable areas of the plant, either driven by experts or working on artificial intelligence to detect problems and fix them. In the lifetime of the plants, who knows, perhaps there won't be any humans on the plant, and it will be self-operating and self-maintaining. Certainly, we should be currently looking at drones for security, to defend against malicious or mischievous attacks by drones themselves. Thank you for listening to me. I hope some of my presentation was of interest to you. And if you like the animation or want to convert your knowledge into a similar data format, then contact me.